Welcome to this second part in this presentation on DirectX11 rendering. We're going to continue adding a few different things to the program and also take a closer look at the shader part of the program. Just as a brief recap, we modified the program to allow for actually drawing what we call an indexed primitive. In this case, we defined a series of vertices where each vertex had a position and color property, and then we defined a series of indices that indexed into those vertices that told us the order in which to draw those vertices. In DirectX, we create corresponding vertex buffers and input buffers. We set the layout which tells the rendering system what the format of the vertices are. We tell it that the layout in this case was the first thing is 3 floats for XYZ position, and the second thing is 4 floats for RGBA color. One of the other things that we added were 2 shader programs or functions. One was a vertex shader and one was a pixel shader, and these are separate pieces of code that are written in HLSL, high level shader language. We have to load and compile those and then set those shaders to the render. One piece of information that in particular that the vertex shader needs in this example is the transformation from world to screen local coordinates. So we have to supply a combined world view and projection transformation, and we do that through what's referred to as a constant buffer. When we completed all that and built and run the program, we get just a simple view of a polygon on the screen. And notice how some of it's off the screen, and that depends on where the camera is and the screen size and where we're looking at and so on. And we'll make a few changes so we'll be able to see more of this. One thing that we notice is we added some of these additional objects, and I don't know if you noticed this, but we did not release them or destroy them. So when we close the program, in the output window, if we're running this in debug mode, Visual Studio in its output window will print out some messages. And in this particular case, it prints out messages something like live producer at, live object at, live object at. And what this means is it's not maybe not the greatest of messages for us, but it's letting us know, it's indicating that there's some live object, some object that's still around that needs to be deleted or hasn't been destroyed properly. And that makes sense. We know we added several things and didn't release them, so we'll just copy these and go to our shutdown function. And notice that we're calling this release com for the depth view and the render target and the swap chain, but not for these new objects like vertex and index buffer that we created. So now we're releasing all these. And in general, in general, we want to release these in somewhat the reverse order in which they were created. Not all of that will be critical, but some of it is. In particular, since we use either the Direct3D device or the device context to make some of these other interfaces, it makes sense to destroy the other ones before we destroy the parent object. So in general, we want to create them in the reverse order in which they were made. So now if we run this and close the program, we don't get those error messages here at the bottom about live objects. Let me just clear this and verify it. So you see that we get the last message that the program is exited with code 0. So if you run this in debug mode, that's more of a normal type exit situation. Well, it turns out there was one other interface that we had failed to release, and that was this raster state. And so now when we've got them all properly released, you see the code here. The output window, when we run this in debug mode, one of the final things that we get is exited with code 0 and no messages about a live object or live producer still existing. One of the next things that we might do that's a fairly simple thing to do is modify this raster state. The raster state did a couple of things for us. One is it set the cull mode to none, so that means that we can see both the front and back faces, which are determined by their winding order, and it tells us to fill in the polygons solid. And another option for this is in wireframe mode. So what we could do is move this into its own function called set raster state. And since this raster state, every time we set it, we have to modify this descriptor and recreate it, we'll want to release it here if necessary. So in this particular case, we release it, create a new one, and set it with the device context. Notice that the definition for release com contains an if test, meaning that if the thing that we pass in this case the pointer to the raster state interface, if that pointer is null, then that if test here will fail and we won't do any release. It's only if it's not null that a release will occur. And what that means is that we have to initialize it properly. We have to make sure that it's initialized. we see that in the so that's something else that looks like it's missing. These variables, all these interface variables, it's a good idea to have those initialized to null pointers. And I'm surprised that I'm not able to find that in the code. I thought it was in the code. Apparently not. So in our initialization function for this program, or maybe in the constructor, yeah, right. So this would be a good place to initialize these. And the idea is that you want to set them all equal to a null pointer value. We don't have to do it for the viewport or the screen width or the screen height. So Visual Studio has a nice tool that we can take advantage of here. We can search for the semicolon and replace it with equals null pointer semicolon, and we can search only in the selection, the highlighted area, and then just go through and replace them. So this is important to set these to null so that if we get a situation where we want to conditionally release a pointer, an interface, we don't want it to point to an invalid, have an invalid address. So by default, variables can have a random value, and you don't want a pointer that's going to be released, you don't want to release something at a random memory location. That's a bad thing. So we have the if test in the release com that checks to see if it's null, but we have to make sure that this is actually initialized to a null pointer or created properly with a call to create raster state. We also have to define this function in our header file. So we're kind of editing in an embedded window here. This is the header file, and we just added the definition for set raster state. Now we need to call this function somewhere. A good place to call that might be at the every time we do a resize. So in the onResize function, this might be a good place to call set raster state. One reason for doing this is that I wanted to be able to make a change, and in particular the change I wanted to make to the raster state was to have a Boolean variable for wireframe mode. And in the initialization function, we can set wireframe to false. When we go to set the raster state, we can add a test there. If wireframe set it to wireframe mode, else set it to solid mode. And to set it to wireframe mode, there's just a constant that's D3D fill wireframe. And we know that wireframe by default is false, but maybe we would like to change that, and we should be able to do that in the key down message. So if we trap So in our message handler, we can trap or handle the key down message and check the message parameter to see if the W key was pressed, and then toggle the wireframe Boolean variable and set the render state. And so what that means is that the W key then would change the raster state. So if I press W, I get a wireframe polygon versus a solid polygon. And it's often useful during development process to see your objects in wireframe mode, because sometimes if you have a solid object, you can see through them, see things in the background or see the backside of your object. That can be a useful thing in development mode to make sure things are working as you intend them to. Let's take a look at the shader programming a little bit more. It's very similar to C programming, but there are a couple of differences, a couple of standard types that are maybe new to you. Something you may want to see in particular, you may want to look at, is the MSDN site reference for HLSL, and you can see the language syntax and the intrinsic functions are probably some of the more helpful things that you could find. So these are some of the functions that you might run across: cosine, dot product, distance between points, so on. We start off in our shader program by defining what our constant buffer is going to be. And you can have more than one constant buffer, but sometimes it's simpler just to put everything in one constant buffer, even if it's needed in both the vertex and the pixel shader. In this case, we have a very simple program, and we've simplified the process. The C++ program is going to combine, multiply the worldview and projection matrices together. So we'll have them all together in a single matrix. Keep in mind that this shader program is a little bit different in that it runs on the GPU. So it's compiled into a separate set of assembly and bytecode designed to run on the GPU. For the vertex shader, it's common to define a structure very similar to a class, but it's a C-style structure that tells us what the format of the vertex is. And this needs to match our definition in the C++ program. So these two definitions here need to match. And we see that they do. I've got a float 3 and a float 4. I've got an XM float 3 and an XM float 4. In the shader language, we have this decoration at the end, and this lets us tell the shader what that variable is going to be used for. And some of the options are position, color, normal, texture. There's some others, but those are probably the most commonly used. So those are special words that the shader knows. Okay, this is for the position of the vertex. Okay, this is for the color of the vertex. When the shader is finished its work, it's going to produce something, and it's going to be a modified vertex that's going to be sent interpolated, and then the interpolated values are going to be sent to the pixel shader. It has a slightly different type. It can have a very different type, but in this case it's just a slightly different type. We're passing it a float 4 and for position and a float 4 for color. And the reason the float 4 for position is that when you multiply a 3-dimension, an XYZ position by a 4x4 matrix, we extend the 3D vector to have a 4th value, and sometimes they call it a homogeneous coordinate. They name it W, and we often give it a value of 1 when we do the matrix multiply. Also note that the decorator, or the name for that position, is different, and this is the responsibility of the vertex shader to convert a position from a 3D position in the world to a 3D position in the view coordinate system. And that's what our worldview and projection matrix multiply does for us. So this is the structure for the input vertex to the vertex shader, and this is the structure for the output of the vertex shader. Here's the vertex shader itself. This name is not critical, but when you compile the shader, so the name of it is not all that critical, but when you compile the shader, you have to use the same name in the C++ program when you compile the shader that you named your shader function, your vertex shader function. All right. The parameter is a vertex in structure, and the return type is a vertex out structure. And so, pretty typical function, we declare a type of thing that we want to return. We return it, and in between the declaration and the return, we do some stuff. And what we're doing is we're taking the position of the input vertex. So we're taking the position of the input vertex, and we're adding that 4th component, that homogeneous W component, as a value of 1, and telling the machine to construct a 4-dimensional vector from a 3-dimensional vector and give it the last value of 1.0. Now that we have that 4D vector, we can multiply it by the combined worldview and projection matrix and store that updated position in the screen view position coordinate system. The color we just passed through, so we don't do any modification to the color here in the vertex shader. We could, but in this case we're not. This line here was just a comment from some testing earlier. And that's all we do with the vertex shader. The pixel shader is even simpler. It takes in an interpolated value from 2 points that are going to generate a line across the polygon, 2 vertices that were going to generate a line across the polygon from the vertex shader. So the output of the vertex shader is the same type as the input of the pixel shader. The return type of the pixel shader is just a float 4 because it's a 4-dimensional color RGBA, and the name of it is SV target. I'm not sure why they use that name, but that's the name that HLSO uses for that. And we're not doing anything with the color, we're just using the interpolated color value as is. So we're not doing anything with it. Again, the name of the pixel shader can be almost anything you want, but it has to match in the C++ code. When you go to compile the pixel shader, you have to specify the name here. So again, here's the code that compiles the vertex shader and the pixel shader, and here's the actual vertex shader and pixel shader here. Just as an example, if we modify the pixel shader, here, you can see that I'm just setting the color to a combination of red and green for all pixels. So every pixel that's rendered by the pixel shader are now going to be a combination of red and green, which is yellow. So we just made a slight modification to the pixel shader. Eventually we'll have a more interesting modification in the pixel shader where we'll look up the color of a pixel in a texture map. We'll do that a little bit later in this course. What happens if you get an error? So just like any other language, programming language, you can get syntax error if you don't type something in wrong. And this is one of the challenging things of doing shader programming, is that we don't have a real development environment like we do for C++ with Visual Studio. This is just a text file, and I happen to be editing it in Visual Studio, but Visual Studio doesn't know anything about shader language. So if I have an error message in here where I forget a semicolon, and I save this file and go to run this again, I get something really odd, and I'm not sure why this happened, but it looks like all the results are in Chinese or something, some foreign language. It's kind of funny. And I'm not sure what happened here. I think it has to do with this buffer pointer actually being a character rather than a wide character. And so I think we can modify this code. I think the error message that we get from the shader compiler is ASCII rather than a wide character or Unicode. So to fix this, we can call, there's a version of message box called message box A, which is an ASCII version, and so we can pass it ASCII strings instead of Unicode strings. And now when we run it, we get a message box. And so what happens is this message box is the result, we could have stepped through this in the debugger, but this is the result of this call right here. So what happened was we tried to compile the vertex shader. There was a failed result and there was error message in the error message blob. And the error message is in, it gives us the file name, shader.txt with a complete path, and it gives us 26 5 to 10 syntax error unexpected token return. So this is giving you the error message for your shader program. If we look at this shader program, it's also giving us the line number. So it's telling us it's at line 26 and columns 5 through 10. So if we look at line 26 and columns 5 through 10, it's telling us an unexpected token return. Well, the problem is not really the return. The problem is that the last line wasn't finished with a semicolon. We can try another example where if we accidentally type in something in the pixel shader and try to run it, you see that we get we still get a vertex shader error. So it was able to see an error in the when we compile the vertex shader. So that's kind of odd. Even though we're asking it to compile the vertex shader, the compiler must also be looking at other parts of the code, and it sees this token question mark on line 32 and it doesn't know what it is. So this is one way of getting some diagnostic or error message from the compiler on your shader programs. As far as I know, Visual Studio won't highlight the different symbols, put a red line underline on them when there's errors. You have to run the program through a compiler and see if there are error messages. And there's actually a command line tool to do that. If you're interested, you can actually compile the shader program on its own from the command line, and it'll generate errors for you as well. So shader programming is kind of challenging for a few different reasons. One, it's a different programming language. The other, it's sort of embedded. We're compiling within another program, and we don't have a dedicated tool for debugging or finding errors in our shader program. There'll be another presentation in the future on trying to do some debugging with print statements and some different outputs to try to figure out what might be wrong with your shader program. We'll have another presentation on that in the future. So that's just the basics of shader programming. We'll see more features later on, but the basic idea is that we have a constant buffer for information that's going into the shader program. We have a vertex input type, an input vertex type, and that's going to be the type of every vertex that we render. We have a vertex output type, which is going to be the result of the vertex shader transforming especially the position from world coordinates to screen local coordinates. We have a vertex shader which receives every vertex that's going to be rendered and returns the modified vertex for the pixel shader. The code is really straightforward. We just take the XYZ position, augment it by 1, multiply it by the world view projection matrix, and pass the color. Pass the color through onto the pixel shader. The pixel shader is even simpler. It takes as an input the output of the vertex shader. It returns a float 4 for RGBA, which is has a special name, SV target, and we're just returning the color for now. The next thing we might want to take a look at is just a little bit of movement. In particular, we might want to move the camera. So notice that when we draw our polygon, some of the polygon is off the screen. Well, one way to change this would be to move our camera forward or back. So in our application, we don't have anything really about a camera except this view matrix. So one thing we could do is to create a variable to store the camera position. And it'll be of type XM vector, and we either have to say using namespace DirectX or prefix XM vector with its namespace. So an XM vector is a three-dimensional XYZ position. And then when we go to create the view matrix, let's see where this is created. We might have to move where this is created. So this is done in the update. That's not a bad place to do that. That's okay. Yeah. And what we'll do is, here the position's a local variable. We're going to move this or delete this and set it to the class level variable that we defined for camera position. So then in the initialization, we'll initialize the variable to something. This is camera position, and we're going to use this XM vector set, and notice that we have the camera position at -20 in the Z direction. So if we go to our message handler, we're already detecting if the W key is pressed. Let's see if we can detect if there's a whole series of key mappings. So VK down is the down arrow key, I believe. And if the down arrow key is pressed, let's move our position, camera position, and this is where it gets a little bit odd, and we need to have a separate presentation on this DirectX math. Notice that we were using the camera position for XYZ storage, and that's fine, but it's not actually stored as a structure or class that has XYZ components. It's actually defined as a special floating point register that has 128, it's 128 bits long and uses 32 bits for a float. So it makes it a little bit challenging to work with when we want to just access the X coordinate. So at some point in the future we'll have a more in-depth discussion on DirectX math, But one way of creating or modifying the camera position is to create another vector and use it to scale. So let me show you what we mean by that. I'm going to create a vector that represents the forward direction. So forward direction is positive Z. Forward direction is positive Z, so I declare this vector this is the W coordinate, the fourth coordinate. We normally don't use it, just set it to 1. This is the XYZ component here, that's the 1. And I'm going to multiply this by something small because I have a fairly high frame rate or message rate. And actually, if I'm going down, I want to go in the reverse direction, so I go backwards by -1. Something else that I did was I added the namespace. It turns out that this plus sign belongs to an overloaded operator for adding two XM vectors. So without including the namespace, the compiler can't see that overloaded operator in the way we've called it here. So at the top of the program, I've added using namespace DirectX. So what this should allow us to do is that if the down arrow key is pressed, it should back the camera up, move the camera in -Z space, or back the camera up. As the camera backs up, we should be able to see more and more of our scene, more and more of our triangle. Let's see if this worked at all. Oh, I've got an error message. Yeah, when I made this matrix, when we make the view matrix, we need to use this new variable that we called camera position. So now here's our scene, and you see that the triangle's cut off. As I hit the down arrow key, you see how we're seeing more and more of the triangle. And the W key toggles it. Sometimes a question comes up as to there's an alternative way of getting user input. The W key and the key down message is one way of getting user input, but this relies on the Windows messaging system and will only allow you to get one input per frame or per Windows message. An alternative to this is to do something, instead of an event-driven input, we can do something more like polling. In polling, what we do is on every update, we ask a slightly different question. We don't have a W parameter because we don't have a messaging system here, but we do have a function that we can use called get asynchronous key state. And here we can ask as many different questions about the state of the keyboard as we want. So we can check to see if multiple keys are being pressed at the same time. So this does the same thing, it just does it at the update, so it does it every frame rather than waiting for Windows to process an input message. And because our frame rate's really high, we may end up moving backwards really fast. Let's see. Yeah, so we move backwards really fast, and I don't have any way to move forwards yet. I didn't program that in there. So we may want to modify this scale factor, or maybe include the delta time variable, which is probably not accurate either. Probably needs to be updated. This should be, we should get this from the timer, the frame time. Something else we may want to do is modify the world matrix every frame. Right now the world matrix is just a identity matrix. So the world matrix is set to an identity matrix and it's not changed. So one thing we could also do in the update function is to change the world matrix to make the object move. So if we go back to our update function, there is a function to rotate about the z-axis, and the angle just looking up to see if the angle's in radians. It is. The angle's in radians. So if I want to rotate a small amount, and then set the world matrix equal to maybe called M world. So let's start off with this. We'll set it equal to so again, we have to get the right data type, going back and forth between this X and XM matrix and our M world, which is a float 4x4. So this is a little bit challenging maybe. Takes a little bit of getting used to work with this. So what we'll do is we'll create an RY matrix, and we can set it to some rotation. And if we make it, say, 90 degrees times math helper pi over 180, that converts it to radians. So that gets us a rotation matrix. And then if we want to set the world matrix to that rotation matrix, So if we want to set this equal to this rotation matrix, we use this float store float. So we store this in that's not right either. That was right. Okay, so we use this function XM matrix rotation about the z-axis, and it gives us this XM matrix type. But our global variable for, or our class level variable for matrix is of a different type. It's of X float 4x4, and so we have to call this store to convert from one, or to copy from one storage format to the other. Again, we'll discuss a little bit more about this DirectX math in the future. It's a little bit awkward right now, but we'll discuss a little bit more. Right now we're just doing a rotation that's 90 degrees about the z-axis. So we should see our triangle rotated. So now you can see that it's rotated 90 degrees. Remember that the red was over here, and now it's moved. The red vertex is moved. So we rotated it 90 degrees. What we'd like to do is rotate it every frame. So one way of doing that, there's a couple different ways of doing that, but one way of doing that is to create a static float angle and set it equal to 0, and then update it every frame so that it moves by some small amount, 1 degree per second maybe. So now this angle, because it's a static, will retain its value from one function call to the next, and we'll rotate it by 1 degree every second, assuming this dt is right. I'm not sure if we're actually using that. Let's take a look. Yeah, we're calling dt with 0.1 all the time, and what we should be doing is calling it with timer dot get frame time. So then one other change that we need to make is that in here we need to change this from our constant value of 90 to our value of angle. And I use the name RY here. Maybe I should just use R, because right now we're rotating about the z-axis, but we'll show a rotation about the y-axis in just a second. So if we do this properly, you see that we get our rectangle, or sorry, our triangle is rotating slowly about the y-axis. and it should be rotating at 1 degree every second, and because there's 360 degrees in a circle, it will take us 360 seconds to rotate, so that's pretty slow. What if we did maybe 90 degrees a second? Then you can see it's much faster, and it should be taking roughly 4 seconds to do a complete circle. So this is rotation about the z-axis, along with our camera being able to move out and wireframe mode. We can change this pretty easily. If we just change this from a z to a y, it'll rotate about the y-axis, which is a vertical axis. And you see how it's rotating about the y-axis. So that concludes this presentation, the second half of our part 2 of our presentation on drawing. I'm looking forward to seeing your programs and the objects you'll create this week. Let me know if you have any questions.